And 68. Yeah. What time's the bell ring? 55. Oh, we got to hurry. How did I waste this much time? Telling all my stories. No, we'll get through more. We'll get through limits involved. Okay. So this one says to use the squeeze theorem, right?
67. Oh yeah, I wrote, this is what I wrote. Zero and zero, and then I wrote, how do you use the squeeze?
Okay, so what I need to think about is the range of sine of 1 over x squared. So I would plug that in. I'd look on my calculator and see what does it go between. What values does the sine of 1 over x squared go between? Y values, bottom to top. You see what I'm saying? I don't have a calculator.
I didn't do sine.
Make sure you're writing.
1 and -1 is only.
That's for sine and cosine of this thing.
Oh, I thought that was negative
So
1 and 1.
sine 1 over, it should still be negative 1 to 1, but if you didn't know.
It's just a straight line. Oh wait, it bends around the axis, around the zero.
You zoom
Wait,
7.
is this not right?
It still goes negative 1 to 1. Yeah. Right.
Sine.
But if you think about it, it makes sense because that part doesn't matter. At the end of the day, a sine function itself, no matter what value you put in, it can only spit out a value between negative 1 and 1. Do you agree? No matter what. It doesn't matter that this is 1 over x squared instead of just x, because no matter what you put in, it can only spit out a value between negative 1 and 1 because it's sine. And that's by definition what sine is. Sine is always that. So this part doesn't matter. It's the fact that it's the sine of something. Well, the sine of something always has to fall between negative 1 and 1. So I'm going to set this between negative 1 and 1. Yes. So now I'm going to give everybody that x squared. I'm going to think about this kind of like an equation or that I'm solving or an inequality I'm solving, and I'm going to multiply everybody's side by x squared. So I have negative x squared less than or equal to x squared sine 1 over x squared less than or equal to x squared. Now I take the limit because if that function has to sit between those two values, then its limit must also have to sit between the limit values here. Now the middle, this is what I'm looking for, right? I don't know what that is, but I do know that with these two, I could evaluate those limits. I can just do simple substitution. That's a basic polynomial function. So if I plug 0 in, I get 0. And 0. Well, if it's between 0 and 0, then it must be 0. Because it said use the squeeze theorem.
What's the point of this squeeze theorem? What is it?
It doesn't prove, it's giving you values, it's giving you a range. Hopefully it comes down to where the numbers are the same on both sides, but a 0 on the bottom. Right. You can't use substitution on this one, and there's no other way to rewrite it. It is, it's kind of, yeah. So if they ask you to evaluate this limit, now if you're on a multiple choice question and you got your calculator, that's easy. What if you don't have your calculator? So it's one of those things. It's not going to come up a lot, but it's a handy one to know. It's a justify thing. Yeah. What else? All of them? We'll just do all of them while we're here. So I should have done one yesterday, and I realize this now, hindsight and whatnot. Well, One where you're only given the equation, not the graph, okay? So understand as you look at this, as I look at this equation, if x is less than 1, right, this is the left side of the graph, do you agree? When if x is bigger than 1, this is the right side of the graph. And I'm assuming they're probably going to ask me questions as I approach the right and the left of 1 here for this one. So x is less than 1, less than's left. So if I'm here, here's where x is 1, right? This first equation is going to be on this side. This second equation is going to be on this side, okay? And however they graph, I don't have to know what they look like right now if they're just asking me limit questions. I can just use the equations themselves. And I'm going to use a substitution type situation. These are important to know because they do give these kind of things to you a lot, especially whenever we get to continuity and we're testing continuity. All right, I don't know why sometimes they can get the notation and the formatting right on these limits and sometimes they can't. They couldn't here. This is 73. The limit as x approaches 1 from the left of f of x. This one's coming in from the left, do you agree? So I'm going to take this one and it's just going to be a substitution. That's it. That's all you have to do. Because that's the one coming in from the left, right? All right. Well, how about 74 where I come in from the right? What do I do? Second equation, because that's the one that's on the right side. So as I come in from the right, and again, these are very, very easy equations that I can just use substitution for. So 1/2 plus 1, 3/2, b. It's one of those things where it would be an open dot, but it's still getting close to that value, right? So this one is coming in, let's see, that's a negative slope. It's going to do something like this. So even though that's an open slope and that point's not defined there, it's still getting closer and closer to it. So you still use it, yes. Now, I'm going to assume one of the questions, yeah, 76. Have we done 75? What's the value of the limit as x approaches? I'll get to that question. Limit as x approaches 1 of f of x. You put what? Y. They're different. They're not the same, so it does not exist. It does not exist because these two are not the same value. From the left, it's different than from the right. It's got that jump discontinuity in it. And then the last one asks you for f of 1. So what is, and this is where you're going to look at which one is it included in and which one is it not. So if I look here, this is the one that includes 1, not this one. So I use this equation. So it would be 2 minus 1, which is 1. 8 to 9. Oh, yeah. 34. Okay. H is, ooh. Go ahead, what? Yeah, you don't need to know it. I'll talk about it though. I need to get my doc cam back out. So this is a true or false, and I mean, obviously the answer was there for you, but it's asking you where, I got to get my doc cam. Yeah. The limit as x approaches c of f of x exists at every c between -1 to 1. Where's 1? 1 is right here. Inclusive or exclusive? Exclusive. So, excuse me, not counting endpoints, it doesn't always have a limit. at every place in between. So we're not worried about here or here, but in between, would the limit from the left always equal the limit from the right? At every point in between there.
Oh, I thought that
Yeah.
was like a point on the graphic.
No, it's interval notation. So from -1 to 1, exclusive. Does the limit exist everywhere there? Yes, because every left-hand limit equals every right-hand limit. That's 44H. Right. Some type of discontinuity, some type of jump discontinuity is what you're looking for, or an asymptote or something like that. Okay, so I ask us, does it exist on the interval from 1 to 3? But again, I'm exclusive, right? So I'm not including the endpoints. If it included this endpoint, it wouldn't be, because that endpoint does not have the same limit, but it doesn't include the endpoints. So from 1 to 3, even though there's a hole here, the limit still exists, because the limit at this hole, still the same thing. Still approaches the same thing from left and right. So that does, so yes. No, it still would be true. You're looking at limits. You're not talking about function definition. You're talking just about the limits. So this, what's this point 2? What's the limit as x approaches 2? 1. Left-hand limit as x approaches 2? Right-hand limit as x approaches 2? It's still the same. It still exists. Everywhere on that interval, the limit still exists. And that's all they're asking. I love it. Do you, Brian? Is it 2 different limits? It's not 2 different limits. You're talking about this one I have circled? Yes, but they didn't include the endpoint. So they said from 1 to 3 exclusive, which means don't look at the endpoint, but everything in between. If it had done this, that's what the parenthesis means. Remember, the parenthesis means do not include it. The bracket means include it. Right. I didn't realize that's what y'all were. That's where you were. Okay, yeah. So this would be a no, but this would be a yes. Because that 1 point, the limit as x approaches 1 does not exist. Because from the left, it's different than from the right. Right. I'm not. What else on your homework? So good. Let's do some infinities, y'all. This is when the rubber meets the road. They're more conceptual. It's not a lot of so whenever we're approaching a certain value, we're able to algebraically manipulate and look and get to there where we can plug in and do an algebra approach. Infinities are not as much of an algebraic approach. They're more of a conceptual approach. Yeah. All right. No, these are not calculators. What y'all keep looking at? I'm not going to lay out the properties of limits because the properties of, do y'all need a break in between, or y'all okay? We literally broke all morning. Go blood. What's wrong? All right, here's what we're going to do. We are going to, I think the first thing that I will do, so calculus is big about definitions and how we can prove certain definitions, and we're going to learn 2 of those today. We're going to talk about horizontal and vertical asymptotes. And I feel like we talked about this a little bit in pre-cal. I at least tried to address this in pre-cal or introduce it. What? I see. I haven't even wrote anything. I was waiting on you. Just talking. I was just talking. I wasn't doing anything. Let me start with an example. What does this function look like? If you graph it. Reciprocal. It's one of those must-know functions. What's that look like? What's the reciprocal look like? Yes. Mm-hmm. This is a great example to lay out both of our definitions here. What happens if I asked you to find the limit as x approaches, let's just say 1 to start with, of f of x? What would you tell me? Not 1, 0, I'm sorry. D and E. Do we all agree? D and E. Why is it D and E? One's going up and one's going down as you come in from, right? But could I do a one-sided limit? Okay. If I really want to. What happens if I approach 0 from the left? Negative infinity. Look at what the graph is doing. Right? As I come in from the left, whoop, I'm approaching negative infinity. I'm going down really, really, really fast. And the closer I get to 0, the bigger negative that number is, if that makes sense. I'm approaching negative infinity. What if I asked you the limit as x approaches 0 from the right? It's positive infinity. Do you see why? Okay. There's your first limit with infinity as far as the limit itself equaling infinity. This is how we define a vertical asymptote. If you have any limit that you take it to some value, it could be the positive or the negative side. It doesn't matter, from the left or the right. Remember, we could approach an asymptote just from one side. It doesn't have to approach from both sides. If you ever get yourself in a situation where you approach just a constant value from either the left or the right, and you get a positive or negative infinity, that is by definition what it means to be a vertical asymptote. And you will have to do that. It may say, you may encounter a question that's like a portion of a part D on an FRQ or something that says, how do you know there exists a vertical asymptote at x equals blah? And you'd have to say, I know because the limit as x approaches that blah equals infinity or equals negative infinity. Because that is by definition of vertical. Does it make sense why that's the definition of a vertical asymptote? All right, is everybody good on vertical asymptotes? Then let's talk about a horizontal asymptote. Horizontal asymptote is a little bit different. What if I asked you to approach infinity here? What happens is x goes to infinity. Now I'm getting into more of an in behavior kind of thing. 0, that's exactly right. It's approaching 0. You see that? As only on the right side, but that's positive infinity, right? So as I get closer and closer to positive infinity, this is getting closer and closer to 0. If I, what? You don't understand? Oh. How about as I approach negative infinity? It's 0 also, right? It doesn't matter if it's the top or the bottom that it's coming from. I think that's what you're looking at. It just matters what it's getting closer to. So this, by definition, is what it means to be a horizontal asymptote. In general, and I'll give you the general form just like I did for the vertical. If you take the limit, what's wrong? What?
Oh, that's true.
Say it again. If it's going down as you approach 0, but as you approach negative infinity. So this side is infinity for x, this side is negative infinity for x. Are you looking at because it's coming in from the top or the bottom? I'm not sure what you...
So like, look.
Show us, Robert. Come show us.
I don't know if it makes sense. This is what he said. Yeah, so like, look, if you're right here, right, and you're going to infinity, you're going this way, right? But it's going down until you get here when you're just back.
But when you look to infinity, you have to look as far to the right as you can. So you don't look that it has two different pieces, because that piece on the left will never go towards infinity. It goes down instead. Is that what you mean? You're talking about the first piece. All right, so if you go towards positive or negative infinity and you get a constant, that is by definition what it means to be a horizontal asymptote. You can also use the squeeze theorem for limits to infinity as well, and all of those properties that we talked about, add, subtract, multiply, divide, exponents, those all hold true here as well. Let's do an example. Believe it or not, that's about all I'm doing in this section. We skip over a lot of stuff here and there because some things are just silly. But it's going to take us a little bit. It'll take you practice getting used to limits. So those are definitions, but now I want to practice with finding some infinite limits. All right, let's see what we got. This is number 3 from your homework. No, this is a new sheet. No, it's actually only 900. So the directions for this one ask me to use graphs and tables to find the limit as x approaches infinity of f of x, the limit as x approaches negative infinity of f of x. So by doing that, what am I looking for? Which kind? Horizontal. I'm looking for horizontal asymptotes by doing that. And then part C says identify all horizontal asymptotes. All right. I'm going to do this one. It says use tables and graphs, but I'm going to use this one as an example to show you how we can kind of evaluate infinite limits a little bit algebraically without graphing them also. So I want you to think about this with me for just a minute. And here's where you really have to put your thinking cap on and get your brain going. We're going to treat infinity like a real number, even though it's not, but we're going to kind of think about it just being a really big number, okay? So keep that in mind as we go. So if I try a substitution type thing here for this, right? So I'm talking about the limit as x goes to infinity of e to the negative x over x. And I want to kind of sub something in there to think about what's happening with this limit. So I have e to the negative infinity over infinity, okay? What happens to a negative exponent? What does that do to it flips it, right? So this is going to become positive and jump down here. Does everybody agree with that? So then I have 1 over e to the infinity times infinity. So I'm just thinking that bottom is huge, right? What happens as you have 1 over huge, just the biggest you can think about? What happens is a very small number. What do you think? And I'm getting smaller and smaller, right? 0. I'm going to say this one is probably going to 0. Does that make sense? What happens is that number in the base, in the denominator, gets bigger and bigger and bigger and bigger. It gets closer to 0. That's why the limit's going to 0. So remember those exponent properties, right? If I have something like this, then whenever this moves down, well, the y was already in the bottom, right? So there's nothing left up top, so I hold the place with a 1. Yeah, that's what I did. I just moved it down. Yeah, if it's a negative exponent.
Oh, it's negative. Oh, I remember this now.
So it equals 0. Now, part B, you're probably going to need a calculator for to kind of look at. But let's see what happens. I'm looking at the limit as x approaches negative infinity of f of x. And so I might try, I always try to substitute in and see if I can reason through it before I do anything else, because I'd really rather do that than I would. So that's going to be positive. So I got e to the infinity over negative infinity. What do you think's happening there? You had to guess. I've got e raised to an infinity. That's it. I would say, well, close to canceling out, but not quite canceling out. Which one's going to be bigger faster? E to the infinity or infinity? E to the infinity. In fact, exponentially bigger by definition, right? So would you say the infinity, would you say that it goes to a value, that it goes to an infinity, that it goes to, I would say infinity also, right? Do you see why? I'm taking something and raising it to the power of infinity besides just having it. See what I'm talking about with the conceptual part of it? You could, but here's the problem when you do that. One, let me just write this. I'm going to take this negative out front so you see what's happening here. And I'm going to say that this goes to negative infinity. We'll check it on the calculator, make sure I'm right. You could, but what's going to happen is you're just going to get a value, and are you going to see it going to, and this would probably be, if they just asked you to evaluate it, it would probably be a non-calculator problem. In this, because you're just getting used to it, they tell you to look up tables and graphs to do it, but eventually you'll be to where you'll have to do it without a calculator. So I'm just trying to kind of tell you how I'm reasoning through it. Because, right, whether you put a negative in the top, the bottom, or in front of the fraction, it's all the same, right? So I didn't want you to worry about that being a negative infinity right now. I just threw it in front of the fraction. Yeah. Brian's like, what is this? Nonsense. Okay. Graph it and look at it. See what it looks like when you graph it. Graph f of x. E to the negative x over x. Because that is what they asked us to do. E to the negative x over x.
It's like this. It's like a normal, it's like a normal like that on the top, right? That's what I said, yeah.
It looks kind of like this. So did we get our limits right? As I go to infinity, this side, what's it approaching? I'd say I got that one right. As you approach negative infinity, So as I go to the left, as far left as I can go, what's it approaching? I would say we got that one right as well. See what we did? Okay, so now, are there any horizontal asymptotes? Where? At 0. By definition, y equals 0 is a horizontal asymptote. When we found this right here is enough information to tell us that it's a horizontal asymptote. Do you? X equals 0. Could you show that with limits? Switching around how? How could you? So you're telling me, let's do this. This is not part of the problem that they're asking, but let's do it since we know. So Robert says we can show that there is a vertical asymptote here, and that x equals 0 is the vertical asymptote. Do we all agree? We can look at the graph and tell that, right? As x goes to the limit, but the limit as x goes to 0 doesn't exist. Does it? There you go. So I could do as x approaches 0 from the right, or I could do the limit as x approaches 0 from the left. They're going to be different. So the limit as x approaches 0 doesn't exist. But the one-sided limits as x approaches 0 do exist. From the right, it's positive infinity. From the left, it's negative infinity. And that tells me, and I only need one of those to justify a vertical asymptote. So this tells me that x equals 0 is a vertical asymptote. Yeah. Yes, no, maybe so. As x approaches 0, the limit does not exist. But all I need to show is just one of these sides, either the right or the left, goes to positive or negative infinity, and that's enough to prove that there's a vertical asymptote there. Because you don't have to, asymptotes, you don't have to approach from both sides. You might have a graph that does this, and this side it's an asymptote, but this side there's not an asymptote there, and that's okay. So you only need to show it approaching from one side. Yes. Yeah. It's just one of the 900. Now you only have 898 because I've done 2 of them with you. Was it, Stella? Was it? Now, Stella Miller, I know you better than that. I love you too, and I know you would do it if I told you that that was the homework. I bet you would. You'd try your best anyway. Okay. Yes, Joyce, you probably would. All right, I got 4 different limits here based on this piecewise graph. Non-calculator. I'm pretty sure that's always get confused. All right. Okay. Sure, try it and see what happens, and we'll come back together. while you write that in your thinking, could a graph or a function have more than one horizontal asymptote? Would it? How? What's the definition of a horizontal asymptote? The limit as x approaches either positive or negative infinity has to equal a number, right? It can have multiple verticals. That's exactly right. Good job. Do y'all see what she said? The question I asked was, is it possible to have more than one horizontal asymptote? Y'all said sure. And I said, well, what's the definition of a horizontal asymptote? The limit as x goes to infinity or negative infinity equals a constant, a value, right? So what happens if I had more than one of those? Could I say that the limit as x goes to infinity of f of x equals 5 and then say, oh, but this graph also has one at 2? No, why? It wouldn't be a function anymore. They'd be right on top of each other. Except what? Ooh, you're right. Yeah. All right, let's go to negative infinity first. Negative infinity, which equation am I referencing? The top equation, right? So I can do a kind of substitution in for this one, or you know what that graph looks like, but let's say you didn't. 1 over infinity always goes to 0. If you ever get yourself in this situation, that always goes to 0. Does that make sense based on what you know a reciprocal function looks like? So what? Yeah. All right. How about positive infinity? Same thing? Nope. -1. Sorry. It's not an asymptote. That's exactly right. Yeah, because it's just a constant function. It's not. How about as x approaches 0 from the left? Well, let's actually think about what it looks like. What happens as you go to 0 from the left?
How do you know the graph?
That one you'd have to just know. Yeah, you can't substitute on that one. Just know what this function looks like. That there's a vertical asymptote there. This is actually, I told you no calculator, but this is actually a calculator problem in here. I just thought you could do this one without one. How about 0 from the right? Positive infinity? Because it goes from the right. Oh, I forgot I'm a piecewise. Jeez Louise. Sorry. Sorry, Robert. I'm sorry. Sorry. Yeah.
I don't understand how it goes wrong with that one. FX is not. I think it only works.
But when you approach infinity, infinity is this piece of the graph, so I have to use that equation. Draw the actual graph. Okay. All right, when x is less than 0, so it's this, and then this. That's the graph we're looking at.
Oh, okay. That one.
There is a vertical asymptote here at 0. Does this? Because we can have asymptotes that now bound pieces of graphs and not. No. Right. Right. Piecewise gets sticky. I know. Shall we do another one? Yeah.